Hi, today this is a video on center of mass. So we know already that Newton's laws, conservation of energy and conservation of momentum, tell us about the motion of point particles. However, most objects or systems aren't actually points, they are some extended objects. So we'd like to know how to use these ideas in order to explain the motion of more complicated objects or systems consisting of many objects. If an object is extended, there can be both external and internal forces, which is different than with point particles. With point particles, all forces were arising from some other thing acting on that particle. Whereas if an object has large or consists of many points, then there can still be external forces due to other things acting on that object, but there can also be internal forces due to various pieces of the object interacting with each other. One way to write this is that the net force acting on an object is equal to the sum of all of the individual forces acting on all of the individual points in the object, which we can write as this sum, right? Some forces are external and some forces are internal. However, we know by Newton's third law that any object that acts on another object has an equal and opposite force on it. So this last term, the sum of all internal forces, are always going to be a sum of pairs. So if a force due to one point in an object acts on another point in an object, then the second point also exerts an equal and opposite force on the first point. So all of those cancel. And so we get that the net force acting on an object is only equal to the sum of external forces acting on it, because all of the internal forces cancel. One nice thing about this is that since force is related to acceleration by Newton's second law, acceleration is related to velocity by the definition, which is also related to position, this means that this division in terms of forces between external and internal forces can also be extended to a division of motion between external and internal motion. For example, if you consider a frisbee that's flying through the air, it acts like a external motion in terms of the force of gravity, right? It follows a projectile path, traveling as if it was a point particle, but it also has a spinning motion about its center. So the internal motion is basically just the object's various pieces interacting with each other, and then the external motion will be characterized by the force of gravity, which is pulling it down as it flies. So the second type of motion, the internal motion, is quite hard to categorize and explain, and we'll see this in a later portion of the course. But for the motion due to the external forces, a system behaves as if it were a point particle. The point particle has mass exactly equal to the mass of the extended object, and the position of this point particle is located at the center of mass, which is basically a weighted average of the mass. So the position of the center of mass, which we call RCM, is the sum of the mass of each individual point times the position Ri of that point divided by the total mass of the object. One quick example of it, which is kind of fun, is consider a boomerang. Boomerangs are obviously twisted, so they have these two arms that extend down from its center. If we actually calculate the weighted average of this, because so much of the mass of the boomerang is down below the center of mass of the object is actually outside of the wood of the boomerang, right? Which is shown by this little red dot. The boomerang is symmetric left to right, so the weighted average of the left-hand side is equal to the weighted average of the right-hand side in terms of horizontal position. So the center of mass is located directly under the center of the boomerang. But the boomerang is not symmetric top to bottom. There's essentially more mass weighted down at the bottom than there is at the top, which is just consists of the center of the boomerang. And so the vertical position of the center of mass is at the red dot, which is outside the boomerang. One quick point, which is kind of nice, is we discussed conservation of momentum last week, and based on the way that we chose to define the center of mass and the motion of this object due only to external forces, that means that this motion automatically conserves momentum. So the momentum of the center of mass is conserved because if the net external force is 0, then the velocity of the center of mass doesn't change. So the momentum of the center of mass also does not change because momentum is simply mass times velocity. So this tells us that the center of mass, that an object travels as if it were a point located at the center of mass in terms of forces and motion. But we also now know that the momentum of the system we can view as the momentum of the point mass plus some sort of momentum with respect to the point mass. And that first piece, the momentum with respect to the center of mass, only changes if there's some external forces. So for instance, if we think about that Frisbee example again, then there is an external force acting on the Frisbee. Gravity is pulling it down. So the center of mass of the entire Frisbee is accelerated down, so the momentum of the center of mass changes. However, if we threw the Frisbee in space, it might still be spinning with respect to its center, but because there's no net force acting on the Frisbee anymore, the momentum of the Frisbee with respect to its center of mass is constant, so momentum is conserved. That's all.